You hear the word voltage thrown around all the time, right? High voltage, low voltage, but what is it actually? It's kind of funny when you think about it. This one little word powers our entire world, but for most of us, it's still a bit of a mystery. Well, today, we're going to pull back the curtain and make it all make sense.
So yeah, let's just get right to it. Have you ever really stopped to think about what's going on when you see one of those danger high voltage signs? What is that voltage they're warning you about? That's the big question, and that's exactly what we're going to break down right now.
All right, to get our heads around this, we're going to use a super simple, but honestly, a really brilliant analogy. We're going to compare the invisible flow of electricity in a wire to something we can all picture perfectly: water flowing through pipes. Seriously, if you can get this comparison, everything else is going to click into place.
Okay, so first things first. In this story of electricity, there are three main characters, three key players you absolutely need to know. Let's meet them.
First up, we've got current. You'll see it written as the letter I. Now, current is the actual stuff that's moving. In our water analogy, it's how much water is flowing through the pipe. It's the physical flow. So, more water moving past a certain point means you've got a stronger current. Simple as that. And here's the star of our show today, voltage, or V. Now, if current is the water itself, then voltage is the push that gets the water moving. It is the pressure. So imagine there's a big water pump in our system. The harder that pump works, the more pressure it creates, and the more force it uses to shove that water through the pipes. That pressure, that is voltage. And our third player is resistance, which uses that cool omega symbol. Resistance is basically anything that gets in the way and slows down the flow. Think of it like a really narrow part of the water pipe, where the water gets all squeezed and has a tough time getting through. It's the obstacle. It's the friction. So let's put it all together real quick. You've got voltage, which is the push from the pump. You've got current, which is the flow of the water. And you've got resistance, which is the squeeze from that narrow pipe. The push, the flow, and the squeeze. Just lock that picture in your head because it's going to make everything else so much easier to understand. All right, so now that we've met our three key players, the next big question is, how do they all relate to each other? Well, it turns out there's a beautifully simple rule that connects them all, and it's called Ohm's Law. Now, don't let the formula V equals I times R scare you. Don't think of this as some complicated math problem. Think of it more like a rule of balance. All it's really saying is that the amount of push you have, the voltage, is determined by how much flow, or current, you can shove through a certain amount of squeeze, which is the resistance. So, let's play with that idea for a second. Let's go back to our water pipes. What do you think would happen if we went over to our water pump and just cranked the power way up? You got it. More pressure equals more flow. If you crank up the pressure, the voltage, but the pipe itself stays the same size, way more water is going to start rushing through it, right? A bigger push gives you a bigger flow. It's a direct relationship. Higher voltage means higher current, as long as that resistance stays the same. Okay, what about this scenario? Let's say we keep the pump pressure exactly the same, but this time we squeeze the pipe and make it narrower. What happens to the water flow then? Well, the flow is going to slow way down, isn't it? Even though the pump is pushing just as hard, that extra squeeze, that higher resistance, makes it so much harder for the water to get through. So the amount of flow, the current, has to go down. It's this constant dance between the push, the flow, and the squeeze. So this might all seem a little theoretical, like a physics lesson, but trust me, understanding this relationship is actually super important for, not getting hurt in the real world. So let's bring this out of the world of analogies and into our everyday lives. So think about a plain old AA battery, the kind you pop into your TV remote. That little guy provides about 1.5 volts. In our analogy, that's a teeny tiny little pump. It's a very gentle push. Now, let's compare that to the wall outlet in your house. That is putting out around 120 volts. Whoa, we're not talking about a little pump anymore. This is a massive industrial strength pump. The electrical push is way, way stronger. I mean, the difference is just staggering when you look at it side by side. A battery has a tiny little push, just enough to power something small. A wall outlet, on the other hand, has a huge, powerful push that can run big appliances. It really is all about the amount of electrical pressure that's available. And this, of course, brings us to the most important question of all. You can hold a battery in your hand, no problem, but you should never, ever stick something into a wall socket. Why? What makes one so much more dangerous than the other?
Well, it all comes back to our key players. See, your body has its own natural resistance. It has its own squeeze. The tiny 1.5-volt push from a battery just isn't strong enough to force much current through your body's resistance. But that massive 120-volt push from the wall, oh yeah, that can easily overpower your body's resistance and force a deadly amount of current, the flow, to go right through you. So get this, the danger isn't the voltage itself. It's about what that voltage is powerful enough to do.
So, if you remember just one thing from all of this, let it be this. Voltage is not the electricity that's moving. It's the potential for movement. It is the electrical pressure just sitting there, waiting to be released, ready to push that current into action the second it gets a complete path.
And that's really what it is. To understand voltage is to understand the force that starts everything. It's the fundamental push in every single circuit. But that kind of leads to another really interesting question, doesn't it? Once you have that push, how does the electricity decide which way to go? What determines the path of least resistance? Something to think about.